Hello friends, last class we discussed initial value theorem, final value theorem, and we also saw how to use Laplace transform to find the solution of networks, and we restricted ourselves to networks with DC excitation. In continuation with previous class, let us try to solve few more examples with DC excitation, and that too with charged capacitor and an inductor having initial current, etc. Later on we will move to a concept called transformed network. To start with, let us consider a simple network. It is a series RLC circuit, and the capacitor is initially charged to a voltage V at 0 minus given by 1 volt, and our aim is to find the current in the circuit when the switch is closed at t is equal to 0. Let the value of resistance be 1 ohm, value of inductance is equal to 1 Henry, and value of capacitance is equal to half farad. Now, when the switch is closed, the three elements R, L, C forms a closed loop, or the elements in the closed loop. So, we can write the differential equation for this circuit in the following manner, that is, the drop across the inductor L into di by dt plus drop across the resistor R into I plus 1 by C integral minus infinity to t I dt is equal to 0. There is no source in the network, so all the three elements are passive elements. So, I can write L into di by dt plus R into I plus 1 by C integral I dt is equal to 0. Now, to solve the network, let us take the Laplace transform of this equation. And if you look at this circuit, the switch is closed only at t is equal to 0. The switch is closed at t is equal to 0, at time instant t is equal to 0 minus, at time instant t is equal to 0 minus, there is no current flow through the inductor. There is no current flow through the inductor, but at t is equal to 0 minus, the capacitor has a voltage V naught is equal to 1 volt. Now, let us take the Laplace transform of this equation. If I take Laplace transform of this equation, we can write L into S into I of s minus I of 0 plus R into I of s plus 1 by Cs into I of s plus q at 0 minus is equal to 0. What is q at 0 minus? Q at 0 minus is the charge, initial charge across the capacitor. Similarly, I at 0 minus is the initial value of current flowing through the inductor. But we know that initial value of current flowing through the inductor is 0, and if I take this term inside, this q naught by Cs term can be written as V naught by S. Q of 0 by Cs can be written as V naught by S, and this minus sign indicates the capacitor, the direction of charge on the capacitor. Okay. Here this capacitor acts, the initial charge and the capacitor acts like a source for the current to flow through the network. So, if I apply these terms, that is q naught by Cs as V naught by S minus V naught by S, and I at 0 minus the current through the inductor as 0, we can rewrite this equation as Ls into I of s plus R into I of s plus 1 by Cs into I of s is equal to 0. That is, this term is 0 and this term is 1, and we can take this term to other side, that q naught by Cs is nothing but V naught by S, which I can take it to other side of the equation. So, if I substitute the initial values of inductor current and capacitor voltage in this equation, we can rewrite this equation in this form. We can write I of s into Ls plus R plus 1 by Cs is equal to V naught by S. This V naught is the initial voltage across the capacitor, which is equal to 1 volt. So, now let us substitute the values of L, R, C and V naught that is given in the problem. We know that R value is given as 1 ohm, L value is given as 1 Henry, C value is given as 1 farad and V naught value is given as 1 volt. If I substitute these values in this equation, and if we simplify this expression, we can get the expression for I of s as I of s is equal to 1 divided by s square plus 2s plus 2. This denominator s square plus 2s plus 2 can be split into two terms. It can be visualized as s plus 1 whole square plus 1. So, this is the mathematical manipulation which we perform so that we can easily find the Laplace inverse of I of s. So, I of s can be written as 1 divided by s plus 1 whole square plus 1. This is of the, so we know Laplace inverse of 1 divided by s plus 1 whole square plus 1 as e power minus t into sin t u of t. So, the solution for current in this network is e power minus t sin t u of t. You can see that this current is a product of exponentially decaying term multiplied by sin t. Eventually, the current, as time t tends to infinity, the current dies down to 0, because you can very easily realize that because this network is a passive network, there is no source in the network. So, the current only as long as the charge is there in the capacitor, this charge will the current through the network. When the charge gets completely discharged, the current in the network eventually has to come down to 0. So, that is why you can get the expression I of t is equal to e power minus t sin t into u of t. Now, let us consider one more example. The circuit shown in figure, steady state is reached with switch K open. Steady state is reached with switch K open. Obtain the expression for current when switch K is closed at t is equal to 0. Assume R1 is equal to 1 ohm, R2 is equal to 2 ohms, L is equal to 1 Henry and the supply voltage V is equal to 10 volts. And it is given in the problem that initially the switch is open and the circuit has reached steady state with switch open. If the circuit has reached steady state with switch open, the equivalent circuit is the voltage source in series with resistor R1, R2 and inductor. When switch K is open, the current which is flowing through R1 has to flow through R2, or these two resistors are in series. So, at t is equal to 0 minus, the equivalent circuit is voltage source in series with these two resistors which is in series with this inductor. But at t is equal to 0 plus, at t is equal to 0 when we close the switch, what happens when we close the switch? When we close the switch, the resistor R2 is in parallel with the short circuit. The resistor R2 is in parallel with short circuit when I close the switch, or the entire current which flows through resistor R1 now flows through the closed switch instead of flowing through the resistor. So, I can say this resistor becomes redundant in the circuit. At t is equal to 0, when we close the switch, there is no current flow through resistor R2 and this becomes redundant. So, your equivalent circuit at t is equal to 0 is voltage source in series with the resistor R1 in series with inductor L. So, instead of having two resistors, when we close the switch, the effect of R2 is eliminated. So, if we write the equation for the network at t is equal to 0 plus, in t is equal to 0 plus, there is no effect of resistor R2 in the network because R2 is in parallel with a short circuited switch, closed switch. So, if we apply Kirchhoff's voltage law for the circuit at t is equal to 0 plus, you can write V into U of t, that is the supply voltage, is equal to R1 into I of t plus L into di by dt. There is no term R2 because now at t is equal to 0, when you close the switch, there is no current flow through R2 and effectively R1 and L are in series. Now, taking Laplace transform of the equation which holds good for time t greater than 0, we can write V by S. V is a DC voltage. So, Laplace transform of V into U of t, we know it is V by S, that is equal to R1 into I of S plus L into S into I of S minus I of 0. What is I of 0? I of 0 is the current flowing through the inductor at time t is equal to 0. So, let us evaluate what is the value of I at 0 plus. We know I at 0 plus is same as I at 0 minus, and let us try to evaluate what is the value of I at 0 minus. To find I at 0 minus, let us go back to the circuit. If you see the circuit at I at 0 minus, the circuit is, it has a voltage source, two resistors R1 R2 in series, and that is in series with inductor L. So, this is the circuit, and it is also specified in the problem that the circuit has attained steady state. The circuit has attained steady state with K open. We know for DC at steady state conditions, the inductor acts like a short circuit. The inductor acts like a short circuit for t is equal to when the circuit has reached steady state condition. So, the equivalent circuit at t when the circuit is under steady state condition with switch K open is voltage source in series with the resistor R1 R2 and inductor acting like a short circuit. So, the effective circuit is V in series with R1, in series with R2, in series with the inductor which acts like a short circuit. So, the current flowing through the network is given by V divided by the total impedance of the circuit. Total impedance is now it has a resistance R1 and resistance R2. So, the current flowing through the network, which is also the current flowing through the inductor, is V divided by R1 plus R2. So, before the closing of switch, the current, since the circuit has reached steady state, the steady state value of current flowing in this network is given by V divided by R1 plus R2. So, I at 0 minus, which is also equal to I at 0 plus, is equal to V divided by R1 plus R2, because since the circuit has reached steady state condition, the inductor acts like a short circuit. So, there is no effect of inductor. So, the current is R1, the current in the circuit at t is equal to 0 plus is given by V divided by R1 plus R2. R1 value is given as 1 ohm and R2 value is given as 2 ohms. So, the value of current and V value is given as 10 volts. So, I at 0 minus, which is also equal to I at 0 plus, is 10 by 3, which is equal to 3.333 amperes. So, now we have evaluated the initial value of current. Now, substituting the initial value of current and getting the expression for I of S, substituting the value of I naught as 3.33 and getting the expression for I of S, we can write I of S is equal to 10, which is nothing but the supply voltage, 10 plus 3.33 S divided by S into S plus 1. So, substituting the value of R1 as L as 1 Henry and I naught is equal to 3.33 and V is equal to 10 volts, and if you simplify this expression, if you try to rewrite this equation and try to get the expression for I of S, you can find I of S is equal to 10 plus 3.333 S divided by S into S plus 1. Now, our aim is to find the current I of t, so we need to get the Laplace inverse of this expression. So, to get the Laplace inverse, we must bring I of S to this form where we can apply Laplace inverse. So, I of S can be written as A by S plus B divided by S plus 1. As I told you in the last class itself, to find the value of A, multiply this I of S expression by S, multiply I of S by S and substitute S is equal to 0. To find the value of B, multiply I of S expression by this term S plus 1 and substitute S is equal to minus 1. So, if I apply this mathematical manipulation, if I solve for the values of A and B, I can find 10 and value to be equal to minus 6.667. You can simplify this, you can get I of S expression from I of S expression, multiply I of S expression with S and substitute S is equal to 0 to find A. Similarly, multiply I of S expression with S plus 1 and substitute S is equal to minus 1 to find B. So, by doing so we have got the expression for A and B. A value is equal to 10 and B is equal to minus 6.667. So, your I of S expression can be written as I of S is equal to 10 by S minus 6.667 divided by S plus 1. So, now we can very easily find the Laplace inverse to get the expression I of t. So, I of t is given by 10 by S is 10 into U of t minus this term is can be viewed as 6.667 into 1 divided by S plus 1, and Laplace inverse of 1 by S plus 1 is e power minus t. So, Laplace inverse of this term is 10 minus 6.667 e power minus t into U of t amperes. So, this is the value of current flowing in the network when the switch is closed at time t is equal to 0. Now, till now we have seen few examples where we excited the network with a DC, and now we will try to read a concept called transformed network. This transformed networks is nothing but trying to draw the networks in time domain. We draw the for a resistor, for an inductor and a capacitor in S domain. So, let us first consider a resistor. In case of a resistor, we know the relationship between voltage and current. The voltage drop across the resistor, if I call it as V of t is given by R into I of t, R into I of t. Now, if I take the Laplace transform of the above equation, we can write V of S is equal to R into I of S. So, I have written the equation in time domain. Now, I have taken the Laplace transform of the equation to get the equation in frequency domain. Now, if I draw the equivalent circuit, I can write the equivalent circuit is V of t is the voltage that is given to a resistor, and the current flowing through the resistor is given by I of t. But the equation in S domain is V of S is equal to R into I of S. So, I can translate this equation into an equivalent circuit. If I translate this equation into an equivalent circuit, this equation can be viewed as a circuit having a voltage source equal to V of S that is given to a resistor of value I of S, and the current flowing through this resistor is resistor of value R, and current flowing through the resistor is I of S. So, V of S is the voltage applied to a resistor of value R through which the current flowing is I of S. So, if I write the equivalent circuit, I can write the equivalent circuit like this. It has a source V of S which is given to a resistor of value R, and the current flowing through the resistor is I of S. So, instead of writing the equation and then taking the Laplace transform of the equation, what we can do is we can directly write the equivalent circuit in S domain. So, this is the transformed network of this equivalent of this circuit. The circuit has a supply voltage of value V of t, R is a resistor, I of t is the current. The equivalent circuit in S domain is it has a supply voltage of value V of S, R is the value of resistor, and I of S is the current flowing through the circuit. Now, let us consider an inductor. For an inductor, we know the relationship between voltage and current is given by the voltage drop across the resistor across the inductor V of t is given by L into di by dt. V of t is given by L into di by dt. Now, if I take Laplace transform of this equation, Laplace transform of this equation is equal to Laplace transform of this term. We know Laplace transform of L di by dt is L into S into I of S minus I of 0. It can be, so V of S is equal to L into S minus I of 0. Now, this I can split into two terms. The first term is Ls into I of S minus the second term is L into I of 0. I can split this equation into two terms. One is Ls into I of S and another term is L into I of 0. Now, is a voltage term, and this term Ls I of s can be viewed as a voltage drop across the element through which the current flowing is I of s and value of impedance is Ls. I can split this term as a drop across the element where the current flowing through the element is I of s and the impedance of the element is Ls. Similarly, I have one more term L into I at 0 minus. I at 0 minus is a constant, it is a value of current flowing through the inductor at time t is equal to 0 or 0 plus or 0 minus. So, this L into I of 0 gives you a constant. This product L into I of 0 is a constant value. So, V of s is the supply voltage, and this term can be viewed as a term in which the current flowing through a element is I of s and the impedance of the element is Ls, and we have a constant voltage whose value is L into I of 0. This term can be viewed as a element having constant term whose voltage is L into I of 0. So, if I write the circuit time domain, we write V of t is the supply voltage, I of t is the current flowing through the inductor, L is the value of inductor, I at 0 is the current, initial value of current flowing through the inductor. Now, if you look at the equation in S domain, you can view this term as a supply voltage of value V of s and current flowing through the network as I of s. And to realize this first term can be realized as current of I of s flowing through an element having impedance Ls. So, I can realize this term as a current I of s flowing through an impedance of value Ls. So, it is Ls. And next term is I do have a voltage whose value is L into I at 0 minus, L into I at 0 minus. So, if you look at this term, the polarity is, the sign before this term is negative, which means that this voltage is aiding this voltage V of s. So, to take care of this sign, we can realize this term L into I at 0 minus as a voltage source of value L into I of 0 whose polarities are in such a way that it aids the voltage V of s. So, if V of s has a polarity minus and plus, L at 0, L I at 0, this is it can be realized as a voltage source with polarities minus and plus like this. So, instead of writing the equation at time domain and then taking the Laplace transform, we can view this as the equivalent circuit, or which we call it as transformed network for an inductor which is carrying an initial current of value I naught. So, the inductor can be replaced by voltage Vs, current flowing through it as Is and having an impedance value Ls, and in series with the voltage source of value L into I of 0 with these polarities. And we can also write the expression for current flowing through the inductor in terms of voltage across the inductor. So, either the voltage current relationship can be written as the expression for current in terms of voltage. In that case, I can write I of t is equal to 1 by L integral minus infinity to t V of t dt. I of t is equal to 1 by L integral minus infinity to t V of t dt. Now, if I take this is again the relationship between the current and voltage in case of an inductor. So, now if I take the Laplace transform of the above equation, I can write I of s is equal to 1 by Ls into V of s plus I at 0 by s. So, if we take Laplace transform of this equation, we know Laplace transform of integral is, if it is Laplace transform of V of t, it is V of s by s plus the value of the integral value of the integral evaluated at t is equal to 0. So, that is nothing but I naught by s, I naught by s. So, I of s can be written as 1 by Ls into V of s plus I of 0 by s. So, this term I of s is the current. So, every term here in this equation has to be a current term. So, this term has to be viewed as a current term. It is a product of V by impedance Ls. I can view this term, this current, as V of s is the voltage drop divided by the impedance Ls, and this term can be viewed as a current source. This term can be viewed as a current source of value I naught by s. If you take this, since I naught is a constant value, I naught is a constant value. So, this current source can be viewed as a constant current source divided by s. This term can be viewed as a current source. This term can be viewed as a where the current flowing through this Ls, current flowing through the impedance Ls is given by Vs by Ls. So, every term here is a current term. So, if I try to write the equivalent circuit from this expression, V of s is the voltage drop across the inductor, V of s is the voltage drop across the inductor, and the total current Is is given by current flowing through this inductor whose impedance is Ls, current flowing through this inductor whose impedance is Ls, and in parallel with a current source whose value is I of 0 by s. So, if I translate this equation into an equivalent circuit, the equivalent circuit has a supply voltage of value Vs, which is exactly the voltage drop across this impedance of value Ls, and Is is the total current drawn, which is given by current flowing through this element. Current flowing through this element is Vs by Ls. Current flowing through this element is Vs by Ls, which gives you the first term, plus the current flowing in this branch. Since this branch has a current source, the current flowing in this branch is I naught by s. So, this circuit in time domain can also be translated into the circuit in S domain like this. So, it has a supply voltage V of s, current I of s, that is the total current, that is equal to current flowing through the inductor of value Ls, or current flowing through this element of value Ls, which is given by Vs by Ls plus a current source. So, there are two equivalent circuits possible. One is, you can realize this inductor as a inductor, the element having an impedance Ls in series with a voltage source, whose value is L into I of I naught, or you can have a parallel equivalent circuit having an element whose impedance is Ls in parallel with a current source whose value is I of 0 by s. So, the inductive circuit can be transformed either into the with impedance in series with the voltage source or an impedance in parallel with the current source. Same way, we can also draw the transformed equivalent network for a capacitor. Now, consider a capacitor. We know in case of a capacitor, the relationship between voltage and current is given by V of t is equal to 1 by c integral I dt. V of t is equal to 1 by c integral I dt, with the limits of integration between minus infinity to t to take care of the initial voltage across a capacitor. If we take Laplace transform of the above equation, we can write V of s is equal to 1 by Cs into I of s plus V naught by s. This is, we can write V of s is equal to 1 by Cs into I of s plus V naught by s. So, if you look into this equation, on this side we have a voltage term. So, every term and on this side of the equation should also be a voltage term. So, this term I of s divided by C of s can be viewed as an element having an impedance of value 1 by Cs and current flowing through this impedance is I of s. So, the value of impedance multiplied by current gives you voltage drop across voltage gives me a voltage term. So, this term, first term 1 by Cs I of s can be viewed as an element whose impedance is 1 by Cs and current flowing through the element is I of s. And every term in this equation is a voltage, even this term should be realized as a voltage. So, this term can be realized as a voltage source whose value is V at 0 by S. So, if you look at the polarities, if this term, the polarities of this term should be opposite to that of the supply voltage, or the polarities of these two terms must be in such a way that they oppose each other. So, if I draw the equivalent circuit, I can write V of s as the supply voltage and current flowing from the source is given by I of s. To realize this term can be realized as a current I of s flowing through an impedance of value 1 by Cs. So, it can be viewed as a term having an impedance 1 by Cs in series with a voltage source whose value is V naught by S. So, voltage source with value V naught by S, and the polarities of this source is in such a way as to oppose the polarities of V of s. So, if I take V of s polarities as minus and plus, here the polarities of V naught by S is minus towards ground and plus on the other side. So, this is one network, this is a transform network which is used to represent the capacitor. Capacitor can be represented by a element having an impedance 1 by Cs in series with a voltage source whose value is given by initial value of voltage across the capacitor by S. We can also draw another equivalent circuit, that is a parallel equivalent circuit in S domain using this particular equation. We know if the current flowing through the capacitor can also be expressed in terms of voltage across the capacitor. So, the relationship is I of t is equal to C into dV by dt. The current through the capacitor is C into dV by dt. Now, if you take Laplace transform of the above equation, how do I write? I of s is equal to C into Laplace transform of dV by dt is S into V of s minus V of 0. Laplace transform of dV by dt is S into V of s minus V of 0. So, this equation can be realized as two terms. I of s is equal to Cs into V of s minus C into V of 0. Cs into V of s minus C into V of 0. So, the C into V of 0 can be viewed as a current source whose value is C into V of 0. It can be viewed as a current source in series, current source whose value is C into V of 0. And this term can be viewed as V of s divided by 1 by Cs. V of s divided by 1 by Cs, which results in Cs into V of s. So, this term can be viewed as a element whose impedance is 1 by and the voltage drop across this impedance is Vs. This term can be viewed as a element whose impedance is 1 by Cs and voltage drop across the element is Vs. So, this term, this equation can be translated into an equivalent circuit having a source voltage V of s, whereas the total current drawn from the supply is I of s, and this total current can be written as the sum of two currents. One is the current supplied by a current source, the current flowing through an impedance of value 1 by Cs. So, this term, it has an impedance 1 by Cs in parallel with the current source whose value is C into V of t. Look at the directions of this current I of s, and if I take this term C into V of t to other side of the equation, it becomes I of s plus C into V naught. So, both I of s and C into V naught can be considered as an incoming current at this node, whereas Cs V of s is nothing but the outgoing current through this element. So, this is the equivalent circuit of the capacitor in S domain. So, when in case of an inductor and capacitor, we can draw two equivalent circuits in S domain. One is a impedance in series with the voltage source, another one is impedance parallel with the current source. Now, till now when we solve the problems, we wrote the differential equation which describes the circuit, and then we translated that equation into equation in S domain. But instead of writing the equation in differential in time domain then translating, we can directly write the transformed network, and when we write the transformed network, we can view every impedance irrespective of whether it is a or resistor, view them as. Here when we solve the problems, we make use of this concept. We write the transformed network of the given network and try to write the equations directly in S domain. Remember, in case of an inductor, if the initial value of current through the inductor is 0, then there is this inductor, the equivalent circuit of inductor is V of S is the voltage drop across the inductor, I of S is the current flowing through the inductor, and its impedance is just Ls. So, any inductor L without initial current translates to a impedance of value Ls. Same thing holds good even in the series equivalent circuit. If the initial value of current is 0, this term happens to be 0, then your equivalent circuit is V of S is the voltage applied to the circuit, I of S is the current, and the impedance of the inductor, the impedance given by the inductance is Ls. So, it can be just viewed as a passive circuit with V of S as the voltage, I of S is the current, and Ls. Whether it is a series equivalent circuit or parallel equivalent circuit, the value of impedance is just Ls. So, L in time domain can be translated into Ls in frequency domain. Similarly, in case of a capacitor, if it is an uncharged capacitor, V of 0 is 0, in that case the equivalent circuit reduces to V of S is the voltage, I of S is the current flowing through the impedance, and value of the impedance is given by 1 by Cs. So, any capacitor of value C in time domain translates to an impedance of value 1 Cs in frequency domain. Same thing holds good here. Again, if you assume the initial voltage to be 0, there is no current source or the value of this current source is 0. In that case, the circuit reduces to a simple network having a supply voltage V of S, current flowing through this network as I of S, and the value of this impedance as 1 by Cs. So, inductor L in time domain translate to impedance Ls frequency domain. Similarly, capacitor of value C farad in time domain translates to 1 by Cs, impedance of value 1 by Cs in frequency domain. Now, let us try to solve this problem by applying the concept which we just studied, that is by writing the transformed network. So, instead of writing the equation in differential in time domain and then translating it, so we are not going to write the differential equation, we are directly going to write the transformed network, and we are going to write the equation from the transformed network which gives you the equations directly in S domain, and we can manipulate the equation and solve the network. So, to do that, let us consider a network. Here it is a network having 2 loops and there is a switch. The problem is determine the current in the inductors L1 and L2 for the circuit shown below. The switch is closed at t is equal to 0 and the circuit has attained steady state before closing the switch. Before closing the switch, the circuit has attained steady state. Let V is equal to 1 volt, L1 is equal to 2 Henry, L2 is equal to 3 Henry, and the resistors R1 and R2 is equal to 2 ohm. Let me try to draw the transformed network. And to write the transformed network, I must know what is the value of initial value of current flowing through inductor L1 and initial value of current flowing through inductor L2. If you look at the circuit, when the switch is open, this circuit is a very simple circuit. There is no current flow through this loop. When the switch is open, there is no current flow through this loop, and current flows only through this inductor L1 and R1. And since the circuit has attained steady state before closing the switch, under steady state condition for DC supply, this inductor acts like a short circuit. At steady state condition for DC supply, the inductor acts like a short circuit. So, if the inductor acts like a short circuit, the entire supply voltage appears across the resistor R1, and the current flowing through the circuit is given by V by R1. So, V by R1 is the current flowing in this loop. V by R1 is the current flowing in the loop before the closing of the switch. That is, if V by R1 is the current flowing through this circuit before closing of the switch, current flowing through the inductor is also same as this loop current, which is given by V by R1. So, the initial value of current flowing through inductor L1 is given by V by R1. And if you look at this loop, this switch is kept open. So, there is no current flow through inductor L2 before closing of the switch. Before the closing of switch, there is no current flow through the inductor. So, initial value of current flowing through inductor L1 is V by R1, and initial value of current flowing through inductor L2 is 0. So, knowing the value of I at 0 minus for inductor L1 and inductor L2, we can draw the transformed network. Since the value of V, the initial value of current through inductor L1 is V by R1, we can evaluate it to be 0.5 amperes, and IL2 we have just now we evaluated it to be 0 amperes. So, knowing these initial values of current flowing through the two inductors, I can write the transformed network. So, look at this transformed network. In transformed network, the resistor in time domain is having a same value of resistance R. So, there are two resistance R1 and R2. Even in the transformed network, a resistance of 2 ohm appear as have resistance having a value of same 2 ohms, and an inductor without any initial current translates to inductor whose value is L into S. An inductor of value L translates to Ls, impedance of value Ls. So, inductance L2 value is given as 3 Henry. So, in frequency domain it translates to 3S, and current flowing in this loop, if we call it as I2 of t in time domain, it translates to I2 of S in frequency domain. So, this loop there is no problem, there is a resistor of 2 ohm, another resistance of value 2 ohm, and the inductance of value 3 Henry can be replaced by an impedance whose value is 3S. And if you look at this 2 Henry inductance, 2 Henry inductance has a initial current whose value is 0.5 amperes. So, we know inductor which is carrying a initial value of current can be replaced by inductor of value Ls in series with the voltage source, whose value is given by L into I at 0 minus. L value is 2 Henry, I at 0 minus is 0.5. So, L into I at 0 minus is equivalent to 1 volt. So, the inductor having initial value of current can be replaced by an inductor having an impedance of value 2S in series with a voltage source whose value is given by L into I at 0 minus. L value is 2 Henry, I at 0 minus is 0.5. So, it translates to 1 volt, and the supply voltage is given by 1 volt. So, V has to be replaced by V of S. So, if the value of this voltage source is 1 volt V of S is 1 by S. So, this is the transformed network. So, now I can view every element as element just impedances without differentiating whether it is an inductor or capacitor, and I can directly write the equation. If I write the loop equation for this loop, there is a supply voltage of value 1 by S, that is in series with 1 volt. So, the total voltage here is 1 by S plus 1. So, the total voltage in this network is 1 by S plus 1, and the current flowing through the impedance of value 2S is I1 of S, whereas current flowing through this resistor is given by I1 of S minus I2 of S, because this is the element which is common between the two loops, first loop and second loop. So, the current flowing through this resistor is given by I1 of S minus I2 of S. So, if I write the loop equations for the first loop, the loop equation for this first loop is 2S plus 2, that is the total impedance of this loop, 2S plus 2 into I1 of S minus 2 into I2 of S, that is equal to total voltage in the loop. The total voltage in this loop is 1 by S plus 1. This 1 is nothing but L into I of 0, IL1 of 0. So, the first equation, the loop equation for the first loop is 2S plus 2 into I1 of S minus 2 into I2 of S is equal to 1 by S plus 1. If I look into the second loop, the total impedance in the second loop is 3S plus 4, 3S plus 2 ohm resistor plus another 2 ohm resistor. So, the total impedance of this loop is 3S plus 4, and the element common to loop 1 and 2 is this 2 ohm. So, if I write the equation for the second loop, the equation for the second loop is 3S plus 4 into I2 of S minus 2 into I1 of S is equal to 0. So, now I have two equations in terms of I1 of S and I2 of S. To solve these two equations, let me put these equations in matrix form and use Cramer's rule to solve these equations. So, if I put the equations in matrix form, the first equation I can write is a matrix whose elements are the coefficients of the terms I1 and I2, and on this side it is the source voltages. So, the first equation in matrix form is given by 2S plus 2, that is the coefficient of I1 of S, minus 2, that is the coefficient of I2, multiplied by a vector of loop currents I1 of S and I2 of S, that is given by 1 by S plus 1. And if I put the second equation in matrix form, the coefficient of I1 term in second equation is minus 2. So, it is minus 2, and the next term is the coefficient of I2, which is nothing but 3S plus 4, and the voltage source value is 0. So, we have put these two equations in matrix form. And if I apply Cramer's rule, how do I apply Cramer's rule? First, let me try to solve for the current I2 of S. To solve for I2 of S, we must replace the coefficients of I2 by this right hand side vector. So, I have replaced these coefficients of I2 by right hand side vector, and this determinant of this matrix divided by the determinant of this original matrix gives me the expression for I2 of S. So, I2 of S can be written as, if I simplify this equation, it happens to be S plus 1 divided by S into 3S square plus 7S plus 2. Now, this is the expression, it cannot be, we cannot take Laplace inverse of this expression. So, we must apply partial fraction and split this term. So, I2 of S can be written as A by S, this 3 can be viewed as a constant. So, it can be viewed as A by S plus B divided by S plus 1 by 3 plus C divided by S plus 2. So, this S plus 1 by 3 into S plus 2, we have got it by factorizing this term S square plus 7 by 3 S plus 2 by 3. I have taken this 3 also outside. If I take 3 outside, this equation becomes S square plus 7 by 3 S plus 2. If I factorize that equation, it results in the term s plus 1 by 3 into s plus 1 by 2, and if I apply partial fraction expansion, I can write this way. And you know how to evaluate the constants of partial fraction expansion. So, if I evaluate the values of a, b, c, a happens to be half, b happens to be minus 2 by 5, and c value is equal to minus 1 by 10. So, if I substitute these values, I 2 of s can be written as 1 by 2 into 1 by s minus 2 by 5 into 1 by s plus 1 by 3 minus 1 by 10 into 1 by s plus 2. So, Laplace inverse of this term is half into u of t minus 2 by 5 e power minus t by 3 minus 1 by 10 e power minus 2 t. So, now with this example we have also seen how to solve a network having 2 loops and how to solve the network by directly writing the transformed network. Tomorrow's class we will try to see some more problems, and we will also see how to solve networks with AC excitation. Thank you.